Hello everyone, welcome to our presentation. Today my teammates Sushanth, Simran, and me, Mingyu Ding, is gonna give you a presentation on RDMA on NetFPGA. Our team name is Team SSD, but before we explain what is RDMA, let's start with an example, analogy, a life story about secure a room in Barcelona. Imagine me and my boss are both traveling out of LA to Barcelona, and we both flying to Barcelona to get this one single room that has the best view and the best deal. We both start flying, but since I'm a poor student, I can only stop at Chicago for my next transfer, where my boss can just stop non-stoply because he's obviously much more richer than I do. Well, my boss will keep flying. I had to transfer again in New York. And well, my boss is at Barcelona and living in his best life in that single room. I have to transfer again in Portugal, Lisbon. And well, I finally got to Barcelona. That single room has been gone. What this life story told us is very well explained our how the internet works in daily apparatus. So me and my boss are just like the data payload, all this data, the streaming data we want to transfer, and all these planes are packets which contains the data payload plus some useful header informations. The route between LA to Barcelona is the data path, and all the stuff that we added is increasing latency little by little. But most importantly, are these stops, Chicago, New York, and Lisbon, are like the layers that we have to deal with in daily internet traffic. How can we help? We found this technology called Remote Direct Memory Access, which is shortened as RDMA. Compared to traditional protocols, which we have to, if we want to send a message from the server to application, as you can see at the top of the screen, we have to layer and delayer between all these protocols such as Ethernet, IP, and TCP UDP. I finally got to the application. But if we have RDMA integrated to this entire process, we can just jump out this process and directly send the message to our application. The RDMA application has been going on in the industry for a while. The current RDMA solutions including ROC, LB, IRAP, and OPA. All these big companies at the bottom of the screen are using RDMA these days. But today we're gonna talk about example on Amazon. So Amazon adapted GPU RDMA in 2020. The uses on the machine learning on their AWS services, which is GPU-based instances. Interestingly, this thing is actually adapted using the technology from NVIDIA. So they promised the 2.5 memory performance improvement and two times floating points performance improvement and up to 50% CPU load reduction. But what are all these numbers telling us is it costs 60% lower cost to train a model, and if they convert those things into a real number on their budget, on their revenue, it's 6.2 billion net revenue increases. And next, my teammate Simran is gonna talk about our solution, how we integrate our solution into this problem and make it better.
Now let's move to our solution. So the proposed solution given by us is implementation of RDMA on NetFPGAs. So this is implemented on RISC-V processor. RISC-V is nothing but an open source instruction set architecture, and one of the few features of our solution is that it is a dual core multi-threaded processor. And a feature that is going to stand out and that will be spoken about in the upcoming slides is kernel bypassing, and that is one of the biggest advantage of our solution. Now, why RISC-V? RISC-V, as I mentioned, it is open source, so it makes a solution more flexible, scalable, and compact all at the same time. So that is why we decided to move ahead with this solution. And I will be talking about how it will be lucrative in the upcoming slides. Now let's have a look at the traditional method. If traditionally we were supposed to exchange data between two nodes using just traditional TCP sockets, then this is something that it would look like. So if node 1 requires data from node 2, what happens is that it needs to send the request to node 2. The data that's there, it will go through multiple layers, protocol layers that are there in the OS. The headers will be added in them as it was shown. Then this will be passed on to the card and onto our layer network. Then it will reach the node 2 where the headers will then be removed. And what happens at node 2 is that there needs to be copying done from the kernel space to the user data space. And all of this takes a lot of time. Then again, headers need to be added. Then this data is sent over the network back to node 1. And again, the headers are removed and node 1 gets the data that's required. So as seen, all this does take up a lot of CPU cycles. It utilizes a lot of time. And our proposed solution is trying to avoid this unnecessary addition of time that also adds on to um, a lot of latency and also decreases the throughput, which is not something that we are aiming to achieve.
So, traditional methods of data copying have two main disadvantages. One, the data is copied from the kernel space to user space, which requires active CPU intervention and ends up consuming a lot of CPU clock cycles. Moreover, the operating system adds in headers at various protocol layers and then eventually removes them at the receiver. So again, this significantly contributes to the latency. So by providing our RDMA protocol, we aim to mitigate these two problems since RDMA provides zero copying mechanism and provides kernel bypassing. So now the real question is, how will a software programmer use this RDMA protocol? So to do this, we are providing our own RDMA API, which involves two instructions. One is the RDMA read and the other one is RDMA write. So an RDMA read would be used to read some data from a remote node, and RDMA write would be used to write some data into the memory of the remote node. So now we'll see the same example with our RDMA protocol implemented. So now again, node 1 wants some data from node 2. So this data is directly sent to our RDMA NIC. Now since it bypasses the operating system, it's the responsibility of a processor to add in all the headers. So it enters the FPGA through the CPU RX queues and then it goes to our core 1. So our core 1 detects that this is an RDMA message, so it now adds in all the protocol headers. So when it enters the pipeline, it enters it through the FIFO SRAM memory and then it goes to the register file, and then eventually at the ALU all the headers are added. So it adds in various protocol headers, and then this packet is again passed on to the output of our FPGA, and then it is sent out of the RDMA NIC through the Ethernet TX queues. Then this packet goes over the network to the RDMA NIC2, and RDMA NIC2 it again enters the FPGA through the MAC RX queues, and then our core 1 will again try to scan this packet and see whether it's an RDMA packet or a normal packet. So if it is detected to be a RDMA packet, so the RDMA header is extracted into the hardware register and all the other headers are removed. So then this data is sent to the CPU TX queue, and now we'll be performing a DMA operation so that this can directly go to the host memory and bypass the kernel. So for doing that, when the packet reaches at the CPU TX queue, it generates an interrupt. It generates a signal known as packet_avail, which shows that a packet is available, and this is an interrupt to the NF2 DMA module. Then the NF2 DMA module puts the N2C data onto the CPCI bus, and then the host uses the RDMA header to get the address of the memory that is to be read. So then the node 2 takes that address and reads that memory location and takes that data, and now it wants to send this data back to node 1. So again, this data would be sent to our RDMA NIC, where again the packet will be encapsulated with all the headers and then sent over through the network to RDMA NIC 1, and again there this packet is decapsulated, and then the data eventually reaches to the node 1. Now I'll be presenting to you a working demonstration of a project. So initially I'll be running a startup script on the control node of NetFPGA. So what the startup script basically does is that it configures the network interfaces, it reprograms the CPCI bus, it loads on a bit file, and after doing that it preloads the instruction memory with all the instructions that are required for a processor. So once the startup script is done, so I'll just be loading the routing table quickly. So now the routing table is loaded. So now we can start benchmarking this. So our demonstration would be divided into two benchmarkings, which is the software benchmark and then the hardware benchmark. So we'll be dealing with the software benchmark now and covering the hardware benchmark later. So to run the benchmark test, we've written a simple Python script which basically runs the various things. So we've given the RDMA read API here, RDMA write API, and all these function definitions are defined inside the RDMA header. And apart from that, we have a simple program running to send a socket message, which sock send, then we can print the application memory space, and we have RDMA read and RDMA write. So before starting the benchmark, I would just simply start a TCP dump on node 0. So now basically what I'll be doing is that node 0 will act as a server. So I'll be running a server script on node 0, and then node 1 will act as a client and will send some message to the server on node 0, and then node 0 will respond back with a message to node 1, and this would be benchmarked. So the operation latency or the time elapsed between this would be benchmarked. So this would be the software benchmarking. So right now I'm going to send a message from node 1 saying we are SSD, SSD being our initials. So as we can see, the time taken is around 7.2 milliseconds. So we can run this multiple times. Now it's 8.6 milliseconds. Now it's 5.3. Now it's 7.7. So we run this benchmark test a lot of times, and then we figured out that the average was around 7.1-ish, and we've noted all the averages and will be presented to you later. So the software test just benchmarks this. So now we'll move to the hardware benchmarking. In this, we'll first try to perform our RDMA write. We're going to try to write some data into node 0's application memory. So before doing that, I'll just print out the contents of the application memory at node 0. So we could see that the application memory of node 0 is initially 0. So now we'll be trying to run RDMA write request. So this is the API which we are using, RDMA write. 000 is the address. So we expect the data to be written here. And after that, we are sending the message we are SSD again. So while doing this, we can also analyze the output of the TCP dump. So initially, we got a message saying we are SSD, which is sent right now while running the RDMA write request. So what it actually does is that the address that I gave 000 can be seen here, and then this is the RDMA identification bits which end with 0D5D, and this shows that it is an RDMA write request. So now if I just try to print out the application memory again, so I expect to see that value written over here. So I'll just do that again. So I can see that this value is written here. So if we check that we send a message known as we are SSD, so W is represented as 77 in ASCII binary, and then E is 65, and so on and so forth. So this exact thing which represents a VR SSD has been written to application memory space. And now we'll again perform a function. We'll perform RDMA read function to see that if we are able to correctly read out this value again. So instead of RDMA write, I'll give a call of RDMA read. Now I'll give the address. So we would want to read out the address 000. So now I expect this value to be shown. So I just run this. So yeah, data successfully read from remote node, and I can see this same value, and we can see that this clearly matches with this value. So the RDMA read is also working fine, and the time elapsed or the time required to perform this is roughly around 5 milliseconds. So again, we run the script like multiple times. We tried benchmarking, we noted down all the readings, and then the final outcome will be presented to you later. So again, now I could just try to write something else. Instead of writing VRSSD, I'll just write SSD, for instance. So once I do that, now I see that here I've got an SSD here. So this is data 73, 73, 64, and then followed by all zeros. So after that, now if I'll just try to give RDMA read request, so to the same, I wrote to 000, so I'll just read 000. So again, I'm able to see that I'm getting 73, 73, 64, and this matches with this. So I'm getting the correct thing.
Now moving on to the real deal, the numbers and the stats. So for both our software benchmark and the hardware benchmark, we had a total of 10 cases that we studied and we arrived to these conclusions. So in case of our software benchmark, the traditional latency came close to around 7.059 milliseconds on an average. And when you see the hardware benchmark, as seen, there was a tremendous drop in the latency and the performance also increased because of this. So talking about the RDMA latency, it was close to 5.025 milliseconds on an average, and this resulted in a total of 28.214% increase in our performance, and therefore it gave us an edge of 2 milliseconds. And mind you, these values are between two nodes. The world that we are in right now, it is heavily and rapidly migrating towards cloud, with cloud customers skyrocketing. Cloud is the future. And because of this, all the big shot companies that are there, all the big players that are there in this industry, they are in this aggressive rat race of trying to have an edge over each other. And when I'm talking about edge, the data centers right now have an intensified demand of high throughput, close to significant amounts of gigabits per second, and ultra low latency rates of less than 10 microseconds per hop. So most companies and most big players are trying to achieve this. One classic example which can portray the industry's sensitivity towards these demands is a New York based firm that was ready to spend close to $400 million just to get an edge of 5 milliseconds when it came to the transmission time. Now that goes on to show how much of a big deal this is and how companies are ready to pay a fortune. When it comes to our solution, as we did present it previously, when it comes to TCP sockets, the latency is close to 7 milliseconds. But when it comes to RDMA, the latency is close to 5 milliseconds, but this 5 milliseconds is between two nodes. Now imagine this in a scenario of a data center which will have millions and millions of nodes. So the advantage is going to be multiplicative. And another thing that is going to make our solution very lucrative is the fact that it can easily be deployed on FPGA boards. And right now the market price on an average of FPGA boards is 5,000 USD. So when you compare that to $400 million for 5 milliseconds, it does go on to show how our solution is economical, viable, scalable, flexible, and is also presenting the results that are required. So all in all, and in conclusion, I'd like to say that RDMA is the best suited way ahead to satisfy cloud customers. And I hope you see how our solution is helping you achieve this, and there is not much complication that's involved. This is our progress report. If you'd like to have a look, these are the references, and this is the end of the slide. Thank you so much for all the time that you've given us today, and I hope you like our solution and are ready to invest in it. and to make yourself ready for the future that is cloud.